Poem from the bottom of a black hole. This is a poem from the bottom of a black hole, a singularity stretched into poetry, grasped by gravity, pulverized by pressure, the words becoming thin wisps that slip ever inward and out of existence. There is no escape from matter or light. Only subatomic energy and white particles seem to confuse the patterns. Confound the predictions and weave the lines of poetry thread thin on the edges of reality before they slip in. This is a poem from the depth of a star's soul, a philosophy persuaded into a vague clarity, allowing no apparent animosity, only light years and luminosity, the flickering fires of a starry sky that spin ever onward and into oblivion. All right, and this is a poem by, not exactly sure who, honestly, somebody, but you can find it on nightpoetry.files.com, .wordpress.com. If I go to this page, no doubt this will actually indicate who what this is. Yeah, so you can go to nitepoetry.wordpress.com. Whomever this poet is, I actually quite like it. There's quite a lot of good stuff here. But, before I continue and blabber on about what exactly, you are currently listening to, maybe that should be actually my primary topic. So you're listening to, and let me switch to this, SG2 on Space, the only weekly space show, I would say. So you can find it, SG2 on Space, www.youtube.com/@shinga/streams, or you can just look up SG2 on Space. Sorry about this little strange vantage point here, trying to do this outside my normal setup. Unfortunately, today, before I go on, let me just say, you can support the show on patreon.com/SG2onspace. And of course, thank you to our supporters and patrons, Kyle Baker, Sam Walsh, and Atum Rod, the last of which Atum Rod was my producer for over a year. And so, thank you very much from the bottom of my heart in this. So this is currently SG2 on Space episode 188, and the topic today is on black holes. Now, as I was saying, I gotta admit that today you may not see the fellow named Dr. Leonard Kramer. He apparently has a life outside of this podcast existence, which is probably a good thing, considering that he's very multi-talented and in many areas, including probably should talk about his art at some point. But that aside. So gotta admit a little bit that the normal Q&A session with Dr. Leonard Kramer is not happening as it stands because, he's not here. So, but I still want to talk about, as the topic suggests, black holes. So, if if we want to exactly go into it, some of you, this is kind of a logical progression from what we talked about last time, which was on supernovas. Now, understandably, last time we talked about two different types of supernovas. So there was the type which was due to the fact of the Chandrasekhar limit in terms of matter building up on top of another star, and then essentially creating that kind of explosion. The second type, which is the death of a star, a supermassive star. That leads to, when you get massive enough beyond what's called a Schwarzschild radius, which we would actually go into shortly, you form what's known as a black hole. So in any case, recall that like a sun, the star, like the size of our sun, for instance, is not large enough, so it's going to end up as a white dwarf. And then beyond that, if a star is more massive than our sun, beyond a certain point, it enters a neutron star. And then stars with stars with masses typically less than 2 to 3 solar masses, which is 2 to 3 times the mass of our sun, become neutron stars. But if you have even more gravity, not gravity, even more mass, then your gravitational collapse is stronger than what even the neutron repulsion could sustain. And so you will collapse towards a zero spatial extent, towards what's known as a singularity, otherwise known as a black hole. So, which you can really never truly observe except when they are emitting X-rays and such. So, an example of this would be, say, Cygnus X1. Let me see if I can actually get something up here. So, let's see here. So, black hole conditions. If we can, okay. Let's see if I clicked this one, Cygnus. Okay, so there's a super giant in Cygnus. So this is what happens when you have like a binary little system, right? So what ends up happening is that you have this blue supergiant star, about 30 solar masses, orbiting this unseen companion. So normally, you would not know it's. So there's actually a couple different ways you would know the existence of a black hole, right? One way is through this. This is one of those most obvious ways. So let me explain this and then talk about some other methods. So in this example, you have a period of 5.6 days in orbit around an unseen companion, right? So you can first of all observe the fact that this astronomers can observe like a star like Cygnus X1, like what is it orbiting around? We don't see anything. Well, what could it possibly be if you don't detect anything from it? And it's very possible. There's a possibility that's a black hole, right? So other thing, you can so what ends up happening is that the mass from here swirls around this and it starts emitting X-rays. So if you observe X-rays from it and you can't see anything there, then there's a good chance that that it's a black hole. And you can also look at a period. So if you calculate the orbital speed, then you can, using orbital mechanics, you can figure out, hey, what is the mass of the other companion that it needs to be? And if it's larger than 3 solar masses, then it has to be a black hole. So it's not like, as in everything is, it's not like a definitive proof, but it's pretty convincing. So in this case, it's also convincing because the emission of X-rays from its location, indication of temperatures in millions of kelvins. This X-ray source exhibits rapid variations with timescales in the order of a millisecond. This suggests a source not larger than a light millisecond or 300 kilometers, so it's very compact. The only possibilities that we know of that would place so much matter in such a small volume are black holes and neutron stars, and the consensus is that neutron stars can't be more massive than 3 solar masses. Okay, so another example is the Magellanic Cloud black hole. So the large Magellanic Cloud is a galaxy close to us. All right. Well, I say close, but it's still literally like 180,000 light years away, but close enough in terms of our local landscape goes. Let's just say. So how do we confirm that? Well, you can observe once again the orbital period of, in this case, there's a binary system as well. So you observe this edge. I used to show the scale for again. Okay, yeah. So observe the spectrum of it, compute the mass and velocity period, estimate the mass of visual from spectral type, and then deduct mass of visual to find the mass of the dark object. So yeah, in this case, in terms of, so this particular object, LMCX3, is one example that that has all the hallmarks of a black hole. I kind of figured, actually, one thing I would like to do is talk about actually the Schwarzschild radius, and I figured we'd do some interactive coding. I think I did that once a while ago on one of our episodes. So you can see here, obviously this website, by the way, Hyperphysics, has a online thing where you could Okay, so first of all, before I dive into like coding, let's talk about what the Schwarzschild radius is. So Schwarzschild radius, I believe the guy who came up with it was named, pretty sure, Schwarzschild, unless I'm completely mistaken. So it's a physical parameter. So it sounds fancy, but it's actually one of the more easier to understand aspects of a black hole that describes one of the fundamental properties. So the Schwarzschild radius, otherwise known as the gravitational radius, is a physical parameter in the Schwarzschild solution to Einstein's field equations that corresponds to the radius defining the event horizon of a Schwarzschild black hole. It is the characteristic radius associated with any quantity of mass. And it's named after the German astronomer Karl Schwarzschild, who calculated this exact solution, for the theory of general relativity in 1916. All right. So you don't have to understand general relativity to be able to understand this equation. Now, to derive it might be a different matter. But to understand this equation, you can see that the gravitational radius, or otherwise Schwarzschild radius, is equal to 2mg over c squared. Okay, so what does that mean, right? So first of all, we'll talk about what the equation is, and then we will I guess plug in some numbers here just as a test, and then let's try the experiment of coding it up. So, so Schwarzschild radius equals, so that's basically the radius of what's known as the event horizon. So past the event horizon, imagine you have a boundary, right, like a sphere. So if you go past it, it's a point of no return. You cannot get out of the black hole, so to speak. So unlike popular perception, it's not that you can't go near a black hole and then you're gone, you're like sucked in, right? It's not, actually it doesn't work like that. So like all objects have an escape velocity. So for instance, for Earth, like if I'm going to try to jump, like I can't jump off the planet, right? I don't get enough kilometers per second. I don't go fast enough to be able to leave Earth's gravitational pull, right? But if you imagine if I launch a rocket, and if it's strong enough, build up enough speed, then it could go off. Like for instance, like any of our interplanetary or stuff that goes to the moon or other places. I mean, as long as it's just not orbiting Earth. But any of our spacecrafts that go to other worlds, it obviously had enough to get off this planet and go out somewhere else. So that's known as escape velocity. So the Schwarzschild radius basically defines what's known as this boundary for a black hole, this radius, which is like, hey, if you go within this radius from the singularity, then the escape velocity will have to be greater than the speed of light. And as most people know, anything that has mass, it's going to be slower than the speed of light, and so you're not going to be able to escape from it. So this really defines, in a way, the size of a black hole, because a black hole itself, like in the center of it, is a singularity, which is a point of infinite density. It basically has zero volume, and it has a finite amount of mass. So that may be the concept of singularity is, to me at least, is kind of hard to understand. Honestly, all physics breaks down at that particular point. So space-time itself is like, it's just like collapses on itself, right? I don't think there's any physics theory that can explain right now, like be able to analyze what actually happens at the singularity itself. But we could at least derive what would happen, like around it, right? So, and here's a picture, like here's like a singularity and the event horizon around there. All right. So without further ado, let's see. We go to here. Let me say 1,000. All right. So for m equals 1,000, what is that? Okay, let's just say it's one solar. Well, okay, let's just say. So the Schwarzschild radius is, in this case, if it's one solar mass, if we want to squeeze one solar mass, which is essentially equal to 0.598 times 10 to the 25th kilograms, then the Schwarzschild radius would be, what is this, 0.008 0.0887285 meters. All right, if we do, like, say, let's do 10 solar masses, then this is 10 to the negative 1 meter. Okay, so then it's 0.088725 meters. All right, you know what? So, I mean, this is cool, but let's see if I can code it up. So I am going to see if, give me 1 second. I'm going to see if I can actually code it up in Python, which is probably my, stop screen. Okay, so let me see, share screen. So realize normally when I'm interviewing Leonard, I can do this while he's talking. So this is a little more difficult since I have to navigate this while also talking, hopefully saying something interesting. Let's see here. So, okay, I think I got something here. Let me just save this thing. Okay, so this I'm just gonna call this. Okay, so this is in I don't know, black holes. I'm gonna just save it in this. This is gonna be called Schwarzschild short. Okay, whatever. Event horizon. How about that? Event horizon.pi. So that's everything plus pi. Not sure if you can actually see this, so I'm gonna zoom in here on this little computer. All right. So author name is Shen here. So I am just gonna start typing things. So this is gonna be called calculate. So Schwarzschild radius calculator. Yep. Okay. So ideally, I mean, it's going to end up with the same result as what hyperphysics showed, except now, you get a nice little script, which you could just run, right? So let's see what the equation was. So the equation, if I flip back to my notes, it is 2mg over c squared. So, so I'm actually going to do this a little backwards, and I'm going to say our gravity, our event horizon, our underscore, let me just do that. Our underscore event horizon is equal to 2 times m times g divided by c double. Okay, so you do this because in Python, I believe if you do that, that is a, that's how you do a squared, actually. So it's not a caret, it's a double star. Okay, so it's a little backwards since normally you're supposed to define the variable first, right? So here, calculate event horizon. So you guys can learn some coding, I suppose, while I'm doing this, which is always great, at least in my view. So gravitational constant, that's a universal constant which exists, which is one of the fundamental constants of physics. If I was wonderfully prepared, I would know what that is. And honestly, gravitational constant, I think it's 6.67, something like that. I forget what order of magnitude is. So it's like 6.67 times 10 to the negative something. I think it's negative 11th. So if somebody could check my math, but I believe it's negative 11. 6.67 negative times 10 to the negative 11th newtons meter squared per kilogram squared. So newtons, so I'm going to put some comments. Newtons times meter squared per kilogram squared. All right. In comments, you could type whatever you want. So I'm using this thing here, even though, like, if it was actual code, I would not be using a caret sign here. All right. So this is gravitational constant. So gravitational constant, universal gravitational constant is that. So gravity is supremely weak, by the way. So normally, like for the other 3 fundamental forces, its constants are much stronger than this. 6.67 times, that's times 10 to the negative 11th here. Speed of light is another constant. So speed of light, I could actually remember that one. 3 times 10 to the 8th meters per second squared. All right, so and then we got to talk about mass, right? So what is the mass? So the mass depends on whatever you want to input in, right? So maybe instead of having it as that, I could do, let me see, import sys. So that way I could do something like your mass is equal to your sys.argv1. Okay, so what this means is that it takes in a user input of sys.argv. Okay, so why is this not, oh, because it's not called mass. I call it big M. Big M equals sys.argv1. All right, so that basically takes the first argument. So 0th argument, if I put 0 here, that would have been just calling the script name itself, which you don't want. You want 1, so that's like the first argument on the command line that you give it. M equals sys.arg1. So, however, we need to probably convert that to a float, because normally when ingested in, it is a string and it's not going to be able to compute it. So we're going to convert that to a float. I might want to do one further thing, because what if somebody does not input anything? So let me do a try and except. This is what I normally do anyways. Better coders than I may end up doing something else. But I would normally be like, hey, if you don't put anything, then I'm going to say enter your mass. Enter mass of object, whatever, in kilograms. All right. So, and then you enter that. That's also going to be a string. So you're going to have to convert it to a float. So do that. M equals float M. All right. So let's see if this works. I'm going to hit F5 here. So, all right. So since I just ran this directly, so you can see the command line interface here, right? It has what is enter the mass of the object in kilograms to the very right. You can see that. So what did I'm trying to think what I should put. I could put probably, I don't know, 0.6 times 10 to the 26. All right, 0.6 times 10 to the 26. So let's just do 0.6 E26. Okay, so that's how you do it. E26. Oh, okay. I forgot to actually print out everything, but thankfully, I mean, this value comes out here, so maybe that's good. So let me actually add one more. So this would be print event horizon radius in kilometers. Is it kilometers or is it meters? It should be in meters, actually. Yeah, meters, because everything else is in meters. So event horizon in meters. So that will be, so I'm just going to print out this, our event horizon. All right. Another thing that we might want to change is, it's really hard to remember. I think astronomers mostly working like solar masses. In other words, like how much, like one solar mass is exactly the mass of our sun, right? So we might want to consider the fact that you don't want to remember like how large something like a huge number like inputted every time, right? So the mass of our sun is actually about 2,000 quetagrams, which is a very funny word. Quetagrams, or it's basically quintillion, or 2,000 quetagrams, or 2 quintillion kilograms. Quintillion is 10 to the 30th power. So it's like basically 1 followed by 30 zeros, right? Like a million is 1 followed by 6 zeros, billion 1 followed by 9, trillion is 1 followed by 12. This is 1 followed by 30 zeros. So it's about 333,000 times the mass of Earth, which is pretty ridiculous. So our sun is fairly massive. And it has a huge radius as well. I mean, it's humongous, right? Like the volume it takes up. Hence why, even despite its mass, like it's not a black hole, because it has it takes up a lot of space. So its actually density is not to the point where it can form a black hole, right? However, let's take our solar mass. So that's basically 2e to the 30th, right? So let me go back to our code here. So let us assume intermassive object in solar mass. Okay, so we can do this, except now let me put what the solar mass in kilograms. So let me do that. So our solar mass in kilograms, m sun. So the mass of the sun, I think I just said, was 2e to the 30th. Okay, so that's in kilograms. All right, so 2 times 10 to the 30th kilograms. All right, so here I could do here mass, okay, float m. All right, so what I'm going to do here is that enter mass of object in solar masses, and I'm going to put just for I'm going to say here solar mass. Actually, you know what? I'm going to assume you already know what solar mass is. Here, I'm just going to say m times equals m sun. So that way you input the mass in solar masses, and then it's just going to automatically, times equal is a shorthand for multiply it by this variable m sun, and then set it back to equal to itself. All right. So now let's see if I can do this. So enter the mass of object in solar masses. Let's just say I choose 1. Event horizon in meters is 2,964 meters. Okay, is that about right? I mean, I could compare with, I suppose, maybe I did. I think that, does that make sense? Actually, one solar mass is one solar. Okay, well, actually, you know what? Let me just say that is one solar mass is 2 times 10 to the 30th kilograms, right? Pretty sure it is. That needs to be okay. Yes. All right. I'm just double checking on the mass of the sun is about 4.4 times 10 to the. Okay. So hyperphysics actually, I think, was incorrect because previously, if I looked at that, it would actually have indicated one solar mass being 0.598 times 10 to the 25th kilograms, which is not true. So one solar mass is actually equal to 2 times 10 to the 30th kilograms. All right. So I'm going to trust actually what I have here. So basically the event horizon in this case is about like 3 kilometers across, which is about the size of like, well, definitely smaller than the size of Houston. So as a, let's see actually how Houston radius. So I'm using Houston's example because that's where I am. So Houston has a radius of approximately 10 kilometers from the center of downtown, I think, to like one of the loops, the inner loop, I think. So in any case, it is okay. So essentially, you know what? You know what might be better is, so I guess the whole point here is that you have to squeeze the entire mass of our sun down to like a sphere that is smaller than the size of like a major city in order for it to form a black hole. So you can imagine how massive a star that needs to be in order to do that. Now, so I said if it's typically if it's greater than 3 solar masses, then we can form a black hole, right? So let's see what happens when you have 3 solar masses. Okay, so I'm going to say here, okay, here I'm going to do just %run. So you can also run it through the command line because I put the sysarg here. So if I put 3 here, okay, so 8,893. So if it's 3 solar masses, then it's going to be 8.9 kilometers. So, maybe I should, I'm just going to do here, I just want to do this event horizon in kilometers, radius in kilometers, why not? And this is basically just this thing divided by 1,000, easy enough. Okay, let me just do this again. And boom. Okay, so 8.893 kilometers. So yeah, so stars, they are, it's really actually not it's not a large amount of what do you call it? An unescapable sphere size, right? So if you go, let's just say a star that's greater than 3 solar mass, that's 3 solar masses, ends up undergoing supernova, and it shrinks down, collapses on itself. Well, the event horizon is is less than 10 kilometers. So as long as you're not within those like 8.893 kilometers away from its singularity, and you're able to travel sufficiently fast, then you're not going to be caught in there forever. However, this is neglecting the fact that you do have what's known as tidal forces. So most likely, even before you get to that point, what ends up happening is that you're going to get stretched extremely thin, and then you're essentially going to be turned into like a human spaghetti, and or whatever it is, and you're gonna, well, you're not going to survive. What ends up happening is that one part of the let's just say it's a spacecraft, one part of it, or your legs, all right, so your leg and head, right, one part of it is going to be undergoing a lot more acceleration than the other. Then let's say your legs are closer slightly, might not seem like huge distance, but with that amount of gravitation, it is a huge difference, and so you're going to be like basically pulled apart. All right. So, and recall, your body is staying together because, well, the cohesion forces there, right? But if it is larger than your cohesion forces, stuff that, that's keeping my skin together, then you're literally going to deform and you get stretched into, you're going to break apart. So, this is not just unique to black holes. I mean, the moon, for instance, causes a tidal force across the diameter of Earth as well, which causes the Earth to deform. It also raises like so hence why like there's tides as well, right? So yeah. Now, how would you actually figure out what the tidal force is? Tidal acceleration. Well, that is a good question. There is actually another equation for tidal acceleration. So we might want to look into that. So the way to do this is here. So this equation, which I'm not gonna, it's on a different screen here, or actually different window. So here's like, I guess I would do the second part of this, since this would be also interesting. And if you want to later in the I'm not going to do it on this episode, but I think later on I will update this code and also look at basically how much acceleration our body is actually going to able to take before it breaks apart. So this will give a good indication of how close you can be to a black hole without breaking into a million little pieces. All right. So okay, so the next part here I'm going to say is, so the first part, and you can do pound percent to essentially indicate different parts of your code that you want to run. So here, this is like calculate event horizon radius. Okay, so maybe I should change short stride radius calculate in other calcs. I will make this a little more general. All right, so here, let us go with calculate tidal force. All right, so the tidal force here, we can figure this out. All right, so this, we could actually use the thing from before. So we're gonna, the tidal force acceleration formula is approximately acceleration equals 2 times g times mass, so times m, and times d. Okay, so d is going to be a new thing. So d, d is, what is d here, right? 2 times g times, oh, I'm not done yet. Let me finish this equation. So once again, I'm kind of like doing things backwards, since normally, some people like define the variables first before they write the equations. I'm doing it the other way around. So 2 times g times m times d divided by r event. Okay, in this case, our event horizon cubed. Okay, so our event horizon cubed. All right. So in the derivation of this, I will leave it for a later time. So okay, so what exactly do we do here? Well, let's see. So what is d? All right, so d is basically the length of the person or the object, actually object or person, whatever it is, in meters. All right, since everything so far we've been using meters. So you can say try. So once again, same kind of deal. So d is sys.argv to, let me just call it the second one that you input in. So turn that into a float as well. All right. So, and then d is equal input. Let me just say enter length of person or whatever object, right? In meters. Okay, so I'm going to do that. D is equal to this. And I'm going to say d is equal to float d. Okay, so I'm going to, you do this kind of calculation, blah. And then I'm going to say print acceleration. Okay, so oh yeah. Okay, so it actually does not necessarily have to be the event horizon here. I think if I do this, it's just going to end up with a huge acceleration that's going to indicate like, hey, even light can escape, right? So probably what I want at this stage is maybe I would actually, instead of doing our event horizon, I will set it as R. R is basically how far away you are, right? I think that's what it is. Or is it? Yeah. R should be how far away something is. So okay. So would that be, yeah? So R. Okay. I think that's right. Yep. So let me just write it here. Okay, so R here, instead of doing that, so R is basically how far away you are from the thing, right? So what this actually indicates, then, this is interesting, that it is not so much dependent on the event horizon radius is literally just dependent on how much mass there is. So yeah. Yeah. Okay. So ours. I'm just gonna call this dot RV3. All right. But you know what? I'm just not gonna do that. I'm just gonna say R is equal to. Let's do this. R equals input enter distance away from singularity. Okay. In this case, once again, it's in kilometers. All right. So you enter that, and R is going to be equal to float R. So we are basically going to request the user to input this. All right, so I'm just gonna run F5. Okay, so enter the mass object. Let's just say we have 10 solar masses. All right, so enter the length of the object in meters. Let's just say a human being is, okay, so America use like imperial units, right? So let's just say somebody's like 6 feet. How far is 6 feet? Is like what, 1.6 meters, let's just say. So 1.6 meters distance away from singularity. Let's just say we're 100 kilometers away. Okay, that's an absurd amount of acceleration. Yeah, so that's in meters per second squared, which may not mean a whole lot to you. So how about we define one more, which is basically acceleration in number of g's. Okay, so 1g is number of Earth g's. So 1g is like how we're feeling now on Earth, right? Like 9.8 meters per second squared. So let me just do a divided by 9.8, and let me rerun this. Do this again. Rerun that. Okay, object mass 10. All right, length of the person, let's just say is 1.6. Like I said, let's just say you're 100 kilometers away, so you're not quite at the so you know you're like more than three times from the point of no return. So you have a ridiculous number of g's. Yep, you are definitely stretched like spaghetti, and like that's like I can't even read that. I should probably output it in scientific units. But 1, 2, 3. Okay, so 6, 9. Okay, so you're like 4.3 times 10 to the 10th. All right, so you're over a trillion, almost a trillion times greater acceleration than what you will feel on Earth. Basically, yeah, you're not going to survive. And yeah, so good indication, right? So I mean that's that's rather interesting. I think to be able to quickly do these these types of calculations. This formula, by the way, I found it on spacemath.gsfc.nasa.gov. So it has some interesting little pages on some basic intros to to like various little math problems. So pretty useful for people who are just interested in or for kids who are not necessarily wanting to do really hard math. But my whole point here is that hey, looking at this, we can quickly figure out actually some of the really fundamental characteristics of a black hole. What I wanted more to talk about is on what a person will actually see as that person falls into a black hole. I think what Dr. Leonard Kramer has some really interesting things he was going to say, but I think what I would like to check out. Let me see if I could do this. So tell me, what would a human see with another human falling into a black hole? So Dr. Leonard Kramer actually asked ChatGPT this question, and it came up with something semi-reasonable. So I think I'm gonna read out what was said that he sent me, so that I'm not like making things up. If I can find it. So the hypothetical thought experiment here is essentially that somebody observes somebody else falling into a black hole, right? So what exactly happens here? So actually, he did not ask ChatGPT. He asked Microsoft AI. So he asked Microsoft AI chat the following question: consider Bob and Alice, since those are so typical names for physics for some reason, very far from a Schwarzschild black hole. Bob is seen in a circular orbit. Alice passes Bob with negligible velocity in free fall directly towards the black hole. Bob observes Alice as she falls. As she approaches the event horizon, Bob sees her clock progressively run slower. Oh yeah, that's another thing I forgot to mention. Strong gravity means clocks go slower, time goes slower. Recall the movie Interstellar. Anyways, as she approaches the event horizon, Bob sees her clock progressively run slower as a result of combined gravitational and special relativistic time dilation effects. The light from her arrives at progressively lower frequency, we might say redshifted. Bob sees Alice's clock run progressively slower until it almost stops and effectively disappears, so that Bob never actually witnesses Alice crossing the event horizon. Okay, now what does Alice see of Bob? Does she not see him rapidly? Does she see him age rapidly? Does she not see the orbit of his period get shorter? She might experience him orbiting 100 times in 1 second of her time. So remember, time is relative, right? The slower your time goes, the faster everybody else seems to be. So for somebody falling into a black hole, when the time slows down dramatically, 1 second of your time might be 1 year of their time. And when you cross the event horizon, at that particular point, so Dr. Leonard Kramer was making the point that your time effectively stops because your clock is running so slow, it reaches this point where like a fraction of a nanosecond or whatever, the smallest unit of time you could think of, is like a million years have passed by in the rest of the universe, right? So is it possible then to like essentially witness the entirety of the beginning, not the beginning, of the progression of the rest of our universe just because you hang out at the event horizon? I mean, that's pretty wild idea. So here's what I think here's what Chat GPT said. So it says this: your question, not Chat GPT. I keep saying Chat GPT. It's Microsoft AI. Your question is very interesting and relates to the effects of gravity and motion on time and light near a black hole. As you correctly described, Bob, who's in a circular orbit far from the black hole, will see Alice, who's in free fall towards the black hole, slow down and redshift as she approaches the event horizon. This is because Alice's clock and light signals are affected by both the gravitational time dilation and the gravitational redshift, which increases as she gets closer to the black hole. Bob will never see Alice cross the event horizon as her clock will appear to stop and her light signals will become infinitely redshifted and disappear from his sight. However, Alice's perspective is quite different. As she falls towards the black hole, she will see Bob's clock run faster and his light signals become blue shifted as she approaches the event horizon. Alice will see Bob age rapidly as his clock will tick faster than her own clock, which runs normally according to her own frame of reference. Alice will also see Bob's orbital period get shorter as his motion will appear faster than her own motion, which is negligible compared to his. Alice might indeed experience him orbiting many times, like going around and around, in 1 second of her time. However, Alice will not be able to see billions of years pass in seconds of her time because there's a limit to how much she can observe from Bob before she crosses the event horizon. The reason for this limit is that Alice's observation of Bob depends on the light signals that he sends to her. As Alice falls deeper into the gravitational well of the black hole, Bob's light signals will gain energy and become blue shifted due to the inverse gravitational redshift. This means that Alice will see Bob's light signals higher in frequency than her own light signals. However, as Alice also moves faster towards Bob, Bob's light signals will lose energy and become redshifted due to the special relativistic Doppler shift. This means that Alice will see Bob's light signals lower in frequency than her own light signals. These two effects will partially cancel each other out, but since Alice's speed is much less than the speed of light, the inverse gravitational redshift will dominate over the special relativistic Doppler shift. Therefore, Alice will see Bob's light signals blue shifted overall as she approaches the black hole. However, as Alice passes near the event horizon of the black hole, Bob's light signals will become infinitely blue shifted due to the infinite inverse gravitational redshift. This means that Alice will see Bob's light signals infinitely higher in frequency than her own light signals. However, as Alice also moves tangentially to Bob at this point, Bob's light signals will also become infinitely redshifted due to the infinite special relativistic Doppler shift. This means that Alice will see Bob's light signals flash briefly at a very low frequency before they disappear. These two effects will exactly cancel each other out at this point, so Alice will see Bob's light signals unchanged in frequency as they pass near the event horizon. However, this also means that Alice would not be able to receive any new information from Bob after this point, as his light signals would become too faint and too delayed to reach her. Therefore, Alice will only see a frozen snapshot of Bob's state at the moment when she passes near the event horizon and not his entire future. In fact, according to some sources, Alice may only be able to observe a finite amount of information from Bob before she crosses the event horizon due to quantum effects that limit how much energy can be transmitted by a single photon. In summary, although Alice will see Bob's clock run faster and his light signals become blue shifted as she falls towards a black hole, she will not be able to see his entire future at an immensely fast pace. She will only see a brief and distorted glimpse of his state at that point and then lose contact with him forever. I hope this answer helps you understand the limitations and paradoxes of observing time and light near a black hole. All right, this is known as a black hole information paradox. Also known as, you can read up on quantum gravity constraints on information transfer, which no doubt has much more advanced math than I'm able to talk about here without doing some research of my own, for sure, 100%. So I'm not even going to attempt it at this point. I think next time maybe I will prepare some code beforehand, and then we can, maybe go into it, right? That might be interesting. So, but in any case, that was an extremely detailed answer, actually, that the Microsoft AI gave Leonard. So next time, I think when Leonard comes back, regardless of our next week's topic, I will bring this up with him, since I am curious on his perspectives on what would happen when, somebody crosses over the black hole. Like, do you observe like infinite number of years, or just a single snapshot in time, because those two different kinds of relativity effects cancel each other out, and once you're past the event horizon, there's no light information. There's no information. Basically, any information is light, right? There's no information that can be transmitted like through this event horizon. So we shall see. I'm curious what he says. So what next? Normally at this point we have a little transition point, right? Because as some of you may know, I am all about well, let's see here. I'm all about talking about the weird stuff. So let me see if I can. Actually, I don't know if this actually shows anything. Let me see here. So the weird stuff meaning what exactly? Well, the possibility of what's out there beyond our solar, aliens. All right, I'm just gonna say it. Why not? Yes, I'm just gonna say aliens. All right, so let's show this little video. You guys can tell me what you think, whether it makes any sense at all. So let me first of all see if I can get this on the screen, and it's up to you to determine whether you actually think this is something that is out of this world. All right, so this is supposedly videotaped over Sydney, right? So silver rotating orb. Silver rotating orb. Oh yes, and Alicia Baker, a close friend of mine, says, "Can you put link to Alice's story, The Paradox?" Yes, I think I would do that. Shortly after this, I will post it on this chat. I mean, what I read was super long, and it was from a text message. So I will. So I will say I will put that on here shortly, and so that I don't have to retype everything. I'm gonna just send a message to myself later. Okay, so all right, let's see what is actually happening here. All right, so silver rotating orb. Okay, like what is happening? Video shot on May 20th, 2022 on the ferry from Manly to Sydney by artist Jody Noas, who's suspected to say unidentified area object. So whatever that thing is, it looks like it's spinning around. That looks like a pretty cool device, actually. All right, brilliant metallic sphere-like object that appears to be spinning. Yeah, I mean, I don't know. So I imagine if Leonard was here, he would probably discount it. For myself, I am less of a skeptic when it comes to these things. So my perspective is, well, maybe. Who knows? I mean, that looks. But honestly, I don't know. I guess it could be made by humans if there's some kind of thing which people have figured out. All right, so UFO casebook. Anyways, all right, so I don't know. Silver rotating orb, right? So I think this is a little more believable than some of the other things, unless somebody just doctored this video, but I don't think so. So not exactly sure what it is, but you know, if somebody else has seen this, in fact, not sure if anybody else was on that day on May 20th, 2022, on like in Sydney. But if you were and you looked up and you saw something, you know, did it look like this? I mean, how would you explain it? I mean, gosh. So I don't know. There's a lot of mysteries out there, that's for sure. All right, so mysteries aside, I'm going to have to say, kind of enjoyed doing this. Also, it was a little impromptu, that's for sure. And also, somebody asked, I don't know who this is. It's an interesting number, 367-824-3289. That looks like a phone number. Wow, interesting. Get Hut and share with us code scripts to GitHub. I think that's what it was. In fact, yes. And you know what? Just because I love doing things live for no reason, not no reason, but here, let me see if I can just briefly share. Let me see if I can. Okay, one moment. This is something I normally don't do, but why not? Okay, so I actually have a GitHub account, and I will here. So let me see. I should share the screen. Share this, please. All right, so share this. Okay. All right. So this is actually where I put a bunch of random scripts, mostly like math and stuff. Like for instance, I was looking at quadratic fits and things for fun. Guess this is what nerds do. But anyways, but point is, I can put that on here, and in fact, I might as well just do it. So let me see, get status. I'm gonna put this on here really quickly. Get add. Wait, does it say it has nothing to commit but untracked? Okay, so get add. Okay, so yes, I have Git on my local computer. So let me see, Git commit m. So I'm gonna say add event horizon code, and then Git push u origin master. Okay, since I don't really bother with branches for this stuff. Okay, refresh the page, and I think it should be there. Yep, it's there. Okay, so black holes, here we go. You can go in here. All right, so you can go to, I'm just gonna just promote my codes just like that. You can go to github.com/shinga86/Python helpers, and then just go into the folder that says black holes, and you can open up like event horizon. And this is what I just typed up live on this stream, right? That's literally, you guys saw me like type up the code. So very simple. All it does is it calculates the short stride radius, which is the radius of event horizon, and it calculates the tidal force, which, as we demonstrated, if you're 100 kilometers away and it's 10 solar masses, it's going to be like almost 1 trillion times greater than the force of gravity here on Earth, acceleration that you feel. So you'll be stretched into spaghetti and like die. So that Alice and Bob scenario, by the way, would be impossible in real life, since we don't have any materials, like including our human bodies, that could sustain that level of acceleration difference. But imagining that you could survive that way before you reach the horizon, then you can imagine that you know, that weird time dilation scenario. So any case, so you can just go to github.com/shinga86/Python helpers and black holes. So I'm gonna put this on the chat so you can, let me see. Python helpers. Yes, I essentially made a repository where I just put dump random Python code, because that's clearly how you do things. Yeah, so you can just go there, and that's where a bunch of code would be at. So you can do that. So, and Jan PL, I don't know who that is, but thank you for watching. Greetings from the Philippines. Okay, wonderful. I don't think I had a viewer from the Philippines before. And Alicia says her sister says Nanu Nanu. Okay, I definitely appreciate that, which is kind of funny. So All right. But I guess that is a huh. Yeah, that's funny. So okay. All right. Okay. With that, I'm going to have to say this has been a fantastic time here, even though, and thank you for the interactions and requests and so forth. Recall the fact that as well that we do have audio episodes. I do need to get more up to speed in updating those. It's been a little while. So I would say it's at least 2 months outdated in terms of that. But you know, if you use Spotify, you could go here, and like I said, the most up-to-date episodes are still on YouTube, so you can YouTube SG2 on Space. And this episode 188. And as always, I will have to say, look up, because you never know what you will see, right? Who knows? I'm not saying you're going to see a black hole, but you can see a UFO. I mean, you could definitely see some stars, some other things for sure. You know, you never know. So look up, like I always say. Thank you again to our past supporters and patrons: Kyle Baker, Sam Welsh, Atum Ron. Support the show, patreon.com/SG2 on Space. We will be back next week, as always, with or without Leonard. Actually, I would say most likely with Leonard. So, all right, take care, everybody. Hopefully you enjoy the fun educational session. And if you have any questions on code or whatnot, I've never asked this, but if you do, I'm welcome to answer them. Or if you want me to code up something else some other time. All right. Okay, so take care, everybody. Namaste.